Welcome to AP Chemistry. In this second video of our unit on intermolecular bonding, we will focus on the types of solids of pure substances possible, given our current sense of both intra- and interparticle attractions. Although we will primarily focus on pure substances, we should be made aware of the types of mixed substances that are also possible. Although this will not necessarily be tested upon, the AP exam makes frequent use of these systems as a background from which to draw. So let us make sense of these. There are three types of mixtures possible based on particle size: solutions, commonly exemplified by aqueous solutions of ionic compounds; colloids, still homogeneous but of significantly larger particle size, like proteins and fats found in homogenized milk; and suspensions, which are plainly heterogeneous. By far the largest category of different mixtures is colloids, in which liquids and solids can be dissolved in gases, like liquid and solid aerosols; gases, liquids, and solids can be dissolved in liquids, like foams, emulsions, and sols; or gases, liquids, and solids can be dissolved in solids, like solid foams, solid emulsions, and solid sols. Again, you should take a moment to read through the examples and make sense of these because of how frequently we will use them as a reference. However, returning to our types of solids, let us begin with ionic solids, which we have already discussed quite significantly. Due to their strong ionic bonding through the lattice arrangement of alternating ionic charges, ionic compounds have high melting points. They resist deformation in their crystalline structure and therefore are considered hard. However, they are also quite brittle, for if a stress is applied to an ionic crystal with enough force to shift the ions in relation to one another, such that anions line up with anions and cations with cations, they will repel and break apart at discrete angles. However, because the ionic charges are immobile in the lattice arrangement, solid salts are insulators, unable to conduct electricity. However, in the liquid state, as well as in aqueous solution, the charges are mobile and therefore well able to conduct an electric current. The next type of solid provided is a metallic solid with delocalized covalent bonding. Recall that metals have significantly weaker electronegativities than nonmetals. Now, what this means for our pure crystalline metal is that it is not made of atoms at all. Rather, it is made of metal cations, in which their valence electrons are freely able to move throughout the material, being attracted randomly to any metal cations nearby. This is what delocalized covalent bonding refers to. Covalent because there is a sharing of valence electrons, but delocalized because this is not occurring in one specific location. But the properties of such metal crystals really do exist in quite a range, based upon the actual arrangement of the atoms in space, their densities, their electronegativities, and the overlapping nature of their d orbitals. Thus, gallium can melt in your hand, and mercury exists in the liquid state at room temperature, while iron and platinum have significantly higher temperatures in order to melt them. Concerning hardness, many metals are assumed to be hard, but lithium and sodium can be easily cut with a butter knife. Thus, in reference to both melting points and hardness, there are a range of properties. However, due to the delocalized nature of the valence electrons within a metal, they are excellent conductors of electric current, since electric charge is able to freely move throughout the crystal. Now, when a molten metal is mixed with another substance, there are two mechanisms that can cause an alloy to form, called substitutional and interstitial. The relative size of each element in the mixture plays a primary role in determining which mechanism will occur. When the atoms are of relatively similar size, the substitutional mechanism occurs where some of the atoms composing the metallic crystals are substituted with atoms of the other constituent. This is called a substitutional alloy. Examples of substitutional alloys include bronze and brass, in which some of the copper atoms are substituted with either tin or zinc atoms, respectively. In the case of the interstitial mechanism, one atom is usually much smaller than the other, and cannot be successfully substituted for the other type of atom in the crystals of the base metal. Instead, the smaller atoms become trapped in the spaces between the atoms of the crystal matrix, called the interstices. This is referred to as an interstitial alloy. Steel is an example of an interstitial alloy because the very small carbon atoms fit into the interstices of the iron matrix. Stainless steel is an example of a combination of interstitial and substitutional alloys because the carbon atoms fit into the interstices, but some of the iron atoms are substituted by nickel and chromium atoms. The next type of solid provided is a network solid with localized covalent bonding. These substances typically have high melting points and are extremely hard due to their distributed network of covalent bonds that bind all the atoms together throughout the crystalline structure. However, since the valence electrons are localized in sigma bonds, charges are not freely able to move, and network solids are considered good insulators. There are exceptions to this, as in the case of when pi bonding is present. Diamond is an excellent example of a network solid, in which pure carbon is interconnected with every other carbon atom by sigma bonds. Another allotrope of carbon is graphite, made of thin sheets of graphene. Graphene, however, has pervasive pi bonding as well, which allows it to be electrically conductive. Quartz is a naturally occurring crystalline network solid of SiO2. However, glass is also made of SiO2, and although it is still a network solid, the arrangement of the atoms is amorphous, not crystalline, being without form or regularly arranged structure. This is the reason that when glass breaks, it does so in a chaotic fracture of the weakest links throughout the entire structure. On this note, we can indicate that plastics form perhaps the largest group of amorphous network solids that are used within our modern world. Wood is also a network solid, primarily consisting of cellulose fibers in a lignin matrix. Now, another way for network solids to conduct electric current is through the formation of p-type and n-type semiconductors. In a pure silicon or germanium semiconductor, each nucleus uses its four valence electrons to form four covalent bonds with its neighbors. Since there are no excess electrons, or holes in this case, the number of electrons present at any given time will always be equal. Now, if one of the atoms in the semiconductor lattice is replaced by an element with three valence electrons, such as a group 3 element like boron or gallium, the electron hole balance will be changed. This impurity will only be able to contribute three valence electrons to the lattice, thereby leaving one excess hole. Since holes will accept free electrons, a group 3 impurity is also called an acceptor. Because an acceptor donates excess holes, which are considered to be positively charged, a semiconductor that has been doped with an acceptor is called a p-type semiconductor, P standing for positive. Notice that the material as a whole remains electrically neutral. In a p-type semiconductor, current is largely carried by the holes, which outnumber the free electrons. In addition to replacing one of the lattice atoms with a group 3 atom, we can also replace it with an atom with 5 valence electrons, such as the group 5 atoms arsenic or phosphorus. In this case, the impurity adds 5 valence electrons to the lattice where it can only hold 4. This means that there is now an excess electron within the lattice. Because it donates an electron, a group 5 impurity is called a donor. Note again that the material remains electrically neutral. Donor impurities donate negatively charged electrons to the lattice, so a semiconductor that has been doped with a donor is called an N-type semiconductor, N standing for negative. Since the bonding of solids formed from the noble gases is so unique, given that it is purely dependent upon dispersion force attractions, it is given its own category. Most of us will never encounter an example of a noble gas in its solid state, since their melting points and boiling points are so extremely low. Finally, we end our survey with molecular solids, made of the crystalline arrangement of molecules attracted to each other due to possible hydrogen bonding, dipole dipole, and dispersion force interactions. Their melting points are generally low in comparison to other solids, and they tend to be soft, since their individual molecules can be shifted quite easily under an applied force. However, since charges are not mobile in the solid state, they are insulators, unable to conduct electric current. We end this video with some discussion on the properties of liquids. We have already discussed that the viscosity of a liquid measures its resistance to flow. Liquids that have strong intermolecular forces tend to have high viscosities. Cohesive forces occur due to the intermolecular attraction between molecules that have similar attractions. Like dissolves like really is short for like electrostatic attractions attract like electrostatic attractions more strongly than unlike electrostatic attractions. This is why nonpolar substances, which are high in dispersion forces, will dissolve other nonpolar substances much more easily than polar ones, like, for instance, oil in relation to oil versus oil in relation to water. Adhesive forces occur in the intermolecular attraction between unlike intermolecular attractions. A liquid spreading out on the surface of another substance is due to this attractive force. Surface tension is the enhancement of cohesive intermolecular attractions due to molecules at the surface being more strongly attracted to the molecules that are underneath them. A convex meniscus occurs when the particles in the liquid have a stronger attraction to each other than to the material of the container, and here cohesive forces are dominant. Conversely, a concave meniscus occurs when the particles of the liquid are more strongly attracted to the container than to each other, causing the liquid to climb the walls of the container. In this case, adhesive forces are dominant, and capillary action can occur when the tube is narrow enough in such a case.